Welcome everybody to Getting Beyond the Basics with Azure Machine Learning. My name is Kevin Fiesel. I'm CTO at Fairgame Inc. And I've got a blog called Curated SQL where I try to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. That's curatedsql.com. What we're going to talk about today is getting a little deeper into Azure Machine Learning. I'm going to start off by quickly refreshing the knowledge that you have on Azure ML. Then we'll talk about code-first programming and that method. We'll walk through model registration and talk about ML flow as a process of storing data as well as models and other relatively important information in source control. We'll build machine learning pipelines and lay out the groundworks for MLOps, an extension of DevOps specific to machine learning. Finally, we're going to show you how to write prediction results to Azure SQL Database. So our agenda starts out with a brief primer on Azure Machine Learning. And for our scenario, we work for a company called Catalyxy Services, which specializes in the sale of propane and propane accessories all across the United States. We have a team of salespeople who travel to different cities across the country in an attempt to sell different organizations and people propane and propane accessories. Well, this is paid business travel, so these people will obviously be paid for their expenses, including meals. There was an issue in 2018 around certain members of the sales staff abusing that trust, and management as a result would like to have us build a machine learning model so that we can hopefully estimate what a good expense report should look like and help them prevent bad expense reports from leaking through. We've decided to use Azure Machine Learning to do this work. Azure Machine Learning is Microsoft's key offering for machine learning in the cloud. And there are quite a few components which make up the entirety of Azure ML. Starting off with data stores. Data stores are connections to where the data lives. So it's not the actual data itself. It is instead a pointer to a location where the data is, like this data lake or this SQL database. Data sets are the data that we'll use to train a model. Now this is getting closer to where you'd think about with the data. As an example, a data set may be a particular SQL query that reads data from Azure SQL Database. Or it could be a particular folder in a data lake from which we're going to retrieve data necessary for training our models. We can train on compute instances. These are hosted virtual machines that have a number of pre-installed data science and machine learning libraries. This makes remote development really easy to do. Compute clusters take you sort of the next step along the process. You want something a bit more powerful to perform training than a single instance or your local laptop or something. A compute cluster will allow you to have potentially multiple machines working together on problems, including machines that have GPUs. After you're done training, they disappear automatically, so you don't have to pay extra money. The Azure ML Studio Designer is probably where you've spent a lot of time in the past with Azure Machine Learning. Many of the introductory or the low-code or no-code Azure ML courses are going to focus on the designer. And this designer allows you to create training and scoring pipelines using a drag and drop interface. It feels like something along the lines of SQL Server Integration Services or Informatica, and that's a pleasant feeling for a lot of developers and data platform professionals. As you run these pipelines, you'll find out that there are experiments that run in the background. And experiments are kind of what they sound like. They let you try things out in a controlled manner. You have different runs of experiments which track your information separately. And that way, I may, for example, have one algorithm I'm trying in a single run, a different algorithm in a second run. Maybe I'm trying a different way of cross-validating data. And I can see how this changes my results over time, grouped by this experiment. Speaking of models, the main goal of Azure Machine Learning and the entire purpose of experiments is really to train a model. And here I've got a set of models that I've built up over different tests over time. Once you have trained a model, you can expose it as an API endpoint for scoring new data. So I may have some sort of endpoint that I've created, which you can query, send in new request information, get back out responses, which are the predicted values. Inference clusters are a place where you can host endpoints for real-time or batch scoring. In other words, what is the machinery that's actually going to be sitting there waiting for requests to come in? Those are inference clusters. So with that, let's jump into our first demo where I quickly rebrief you on what the notions are in Azure Machine Learning. In this first demo, we're going to have a brief overview of the Azure Machine Learning Studio experience. Just to remind you if you've seen it before, and if you haven't seen it before, give you a quick idea of what I would consider the low-code, no-code basic experience. And in here, the first thing I'm going to look at is data stores. Inside these data stores, I've got a few, but the ones that will be important for today, expense reports and this default workplace blob store. So this is created by Azure Machine Learning. It's just a blob storage account somewhere. Expense reports is a connection to an Azure SQL database that I own. So with those two data sources, we can create data sets. And the data set that I'm going to work with here is expense reports. This is a query that pulls in expense report data from this table expense report, joined to categories, joined to employees, and it has some information about employee ID and name, expense categories, dates, and years. Nothing too crazy. Once I have this data prepped, I can go to the designer and select create a new pipeline. For the sake of time, because this isn't a low-code Azure Machine Learning talk, we're going to jump to the completed product, this expense report fraud analysis. And inside here, what I have is what I would consider a fairly simplistic but complete workflow for an Azure Machine Learning exercise. We have our raw data coming from Azure SQL database, and we split that data. Now, we're going to split the data earlier than 2017, or before or equal to 2017, into the first bucket, after 2017 in the second bucket. For the prior to 2017 data, we'll train a boosted decision tree regression model. The regression algorithms are not exactly the same as what you'd get in scikit-learn, so that's still okay. We train this model, we score the model off of the data after 2017, and then we can evaluate the model and see how it did. So submit this, publish it to an inference pipeline. That inference pipeline is fairly simple. I could create a web service here, score the inputs of the web service, and write it out as an output from the web service. Submit this, push it out, and I'd be able to get a published web service, mostly using point and click technologies. Welcome back from our first demo. Now we're going to talk about code-first programming. If we use the Azure Machine Learning Studio Designer, that works well enough to get started, to understand some of the base concepts available to us. But very quickly, we're going to want to move to code. We'll want to manage that code, deploy that code, store it in source control, have it available in the case of a disaster. So there are two methods Azure Machine Learning supports for writing and executing code that we're going to cover today. Method number one, executing code via Jupyter Notebooks. Method number two, executing code from a machine using Visual Studio Code. And that machine can be a local laptop or desktop machine. Azure Machine Learning has some built-in support for Jupyter Notebooks, which will execute on compute instances. We have up here CS Compute 2. That is a compute instance which I've created in Azure. Once that instance is turned on, I'm able to execute code from it. The code that I'm going to execute is actually a big part of the Python SDK. So Azure Machine Learning has a software development kit specifically for Python that you can use to work with all of those different constructs we talked about in the primer, as well as more. There used to be an R SDK, but that's been deprecated. And instead, the recommendation is to use the Azure command line interface and push out R-based code. So you can still write R code, you can still work with R code, it's just a little harder to do. With that in mind, let's jump to our next demo where we talk about code-first programming in Azure Machine Learning. In this demo, we are going to take the same ideas that we looked at in the designer and apply them in code form. The first step, maybe that baby step toward automating your own processes, toward getting a fully fleshed out machine learning pattern, is to create notebooks. And you can create notebooks in this Azure Machine Learning Studio. Now, a notebook does require some compute. So we'll check compute out here, and I have the CS Compute 2 instance already started. If you have to wait for it to start, that'll be a few minutes. If you have to create one, it's really easy to do. You select new, couple of steps, choose the machine you want, and it'll be started up. I also want to point out that I've got a few compute clusters, specifically the CPU cluster that we'll probably use later on during our demos. Just setting up the scenery for you. So let's return back to notebooks. And the notebook I want to look at is called Expense Reports Code. You're going to be able to get a copy of this notebook, so just pay attention to what's happening rather than trying to furiously copy down the code. What we're going to do is access the Azure Machine Learning Python software development kit, the Python SDK. Inside the Python SDK, we have a lot of different classes and modules that we can work with. So, for example, workspaces, environments, data stores, data sets. You can see many of those same names over here. We have experiments and data paths. There's a fair amount going on in this. And also, I'm not going to use an Azure Machine Learning algorithm to train my model. I'm going to use the decision tree regressor in scikit-learn. And so I'll import that. I'll also import things like mean squared error from scikit-learn. We'll import a few other libraries as well to help us out with this. And then we'll load a workspace from the configuration. Because we're working with a compute instance and a notebook that is set up on that compute instance, there's already a .azureml/config.json on this compute instance. Inside that config.json is enough information to give us the ability to connect to our default workspace. So if I run that, it just takes a moment and we've loaded up our workspace. Inside that workspace, I can get a data store named Expense Reports. That Expense Reports database, remember, just is a Azure SQL database and is preloaded as a data store. Once I have that data store loaded, I'm able to query it. It's Azure SQL database, so I can write SQL queries. Well, my query will look very similar to the data set that we had before, But I decided I wanted to take it the query route so I can show you how to split training and test in one way. So here is a query that is very similar to what we saw in the data set in the first demo, but where year is less than 2017. Then I'm going to assign data types, and I'm going to change the path. Instead of being less than 2017, let's say greater than or equal to 2017. And that'll be the testing query. So I replaced the value in here, and that's how I changed from training to test. And for the training data set, we're going to load it from a SQL query using this data type configuration and convert it to a pandas data frame. And we're going to do the same thing for the test data set as well. Let's run this cell. It'll take a few seconds to finish up. Assuming that everything works well, we can move to the next step. In the next step, we're going to begin to put together the pieces that will be important. We have an experiment. The experiment is simply a way of connecting together different runs of our machine learning training. And sort of, if you think of the notebook idea, labeling them in the same section of a notebook or putting them in the same folder. And then we have individual runs. So we're going to start logging a run. We'll train our decision tree regressor and fit using our inputs expense category ID and expense year. And then our training amount will be the thing we want to predict. So this gives us a trained model. Then we can perform predictions using reg.predict. And what I'm going to do is I'm going to call reg.predict on the testing data, feeding in expense category ID and expense year. And I'm going to add a new column called amount prediction and convert that to a data frame. So pred is just a single column that reads amount prediction and is the prediction. I'm going to concatenate that with our testing data. So think of it as combining together all of the test columns and then appending one extra column, amount prediction. Once I've got that in place, I'm going to calculate the mean squared error of my test amount versus the predicted test amount and take the square root of that. So this is root mean squared error. The nice thing about root mean squared error is that error terms are in the form of the thing that they are measuring. We're measuring amounts of expense reports, which means that our root mean squared error will also be in the amount of an expense report, so the dollar amounts, and we'll be able to compare and say, oh, well, this is $12 off or $15 off or whatever. After I do that, I'm going to log each employee's name, expense category, and root mean squared error. As I'm doing this, let me run the cell as I explain it. That way, we'll see when everything's done. We can see that the root mean squared error is just over $14 in this case. Not that great, but that's okay. And we'll see why in a moment. So for each employee, we're going to group the data by employee name and expense category and loop through and get the root mean squared error of that group's amount versus predictions and show the employee name, the category, root mean squared error, and also log that information as well. Then let's save the model as output/model.pickle and essentially write it out to a file. So write it out to this pickle file. Once I've done that, I can complete the run and actually register this model as the expense reports notebook model. Now that I've done this, let's take a quick look at what has happened. So first I want to look at the models and we're going to see this expense reports notebook model. And I have an expense reports notebook model right here. This is actually version 2 for me because I've run through this before. So this is the new version I just created. Then inside experiments, we have the expense reports notebook, and the latest run is run number 2. If I select that run, I'm going to check out the metrics, and I've already selected different employees and inexpensive cities. Within this data set, there are 3 categories of city: inexpensive, moderately expensive, and expensive. And as people travel around selling their propane and propane accessories, in the inexpensive cities, you don't have to spend very much on a meal. These might be rural areas where you go get barbecue for a few dollars. And we can see that many of these people have expenses somewhere around $5 per meal in the inexpensive city. But we've got some people who are in the $15 range. And it turns out that these were the people who were padding their expense reports to get to the maximum level before they had to send in a receipt. And that was the fraud. This talk doesn't really focus on the fraud side of it. It focuses more on the building out a model side of things. So we have our results here. And this is also why I was okay with the root mean squared error being somewhat high, because it turns out the reason it's high is because there was fraud in the data. But with that said, we have our experiment, we have a model that's been written out, and all of this happened strictly through code. I didn't have to go through the designer, I didn't have to drag and drop anything. Welcome back. Let's keep on talking about execution of code. And let's say I don't want to simply have this code running in a compute instance. I'd like to be able to maybe work on it while I'm offline, or work on it within the confines of my own corporate environment. You can execute code locally. And the way that you're going to want to do that is actually through the Azure Machine Learning extension in Visual Studio Code. So with this extension above, you're going to be able to connect to and work with the workspaces in Azure Machine Learning, and you'll also be able to even set things up so that you can execute code from your local machine. The extension will give you direct access to different objects within your Azure Machine Learning workspace. And I'll show you an example of that in a little bit. But first, I'd like to talk about MLflow and give you an idea of where this becomes really beneficial. MLflow is an open source product that is designed to manage the machine learning development lifecycle. So in other words, data scientists can train models, can register models, deploy those models to some server, and manage updates to the models as they change over time. MLflow was developed by Databricks and is still most heavily used in Databricks, but its utility definitely goes beyond that and is included in Azure Machine Learning in a couple of ways. So MLflow is made up of 4 products that work together as a whole. The first product we're going to talk about is MLflow Tracking. MLflow Tracking will allow a data scientist to work with experiments and work with the runs in experiments. We talked in the primer about Azure Machine Learning experiments and runs, and these notions are effectively the same. For an MLflow experiment, you have a run which can log parameters, versions of libraries used, evaluation, inputs, outputs, generated output files, maybe images that are created as a result of this. And you'll have the ability to go back in time, understand what has happened, and experiment with different sets of inputs, seeing how that changes your model. MLflow Projects is a way of packaging up code and deploying that to different machines. So essentially, so that you don't have the problem of it works on my machine, or it works in dev, but it doesn't work in prod, trying to reduce inconsistencies. And you can do that, for example, by setting up a Conda environment, or maybe by creating a Docker image, or even the way that you're installing code on a particular system. MLflow Projects helps you out with that. The third tool is MLflow Models. MLflow gives you a standard format for packaging models, and that standard format is cross-compatible with a lot of really common machine learning libraries. For example, scikit-learn, PyTorch, TensorFlow, Keras, ONNX. These things, these different projects, can all be put together using MLflow models, and for all of them, we're going to be able to serialize the models, store them in a way that we can access them later, regardless of whether it was scikit-learn or TensorFlow or ONNX that created the model. We'll be able to use MLflow to deserialize that and work with it. The MLflow model registry will let a data scientist register a model. So you have the serialization and deserialization of models, but then the next step is how do we save these models in a place where operations can then deploy the models to a production environment, either through a REST API that serves the model, so you send in a request, you get back out a response, or batch inference where you send in a whole bunch of input data, you get back a whole slew of output results. How does this work with Azure Machine Learning? Well, there's a couple of ways that this can work. If you're already using MLflow, if you have an MLflow tracking server already set up and you want to continue using it, then Azure Machine Learning allows you the ability to connect to that remote tracking server and to feed information into it. That said, Azure Machine Learning was intentionally designed to be very similar to MLflow, emulating many of its key capabilities. So if you want to stay within the confines of Azure ML, you'll still get many of the benefits that you would get with MLflow. So for example, with tracking, experiments in Azure ML are our analog to ML tracking. And we have the same notions of experiments and runs, we have inputs and outputs, we have all kinds of interesting information. We can track the details of different metrics that we've logged. Here I have a snapshot, you can see it's highlighted here, which shows the actual training code that was used for a particular run of a model. We can track output files, parameters passed in. We can track contents of Python scripts. So we have a lot of different images and different inputs and outputs that we're able to maintain using MLflow tracking. With projects, if you're using MLflow projects to package up your code, you can execute that code on Azure ML Compute. There's a direct ability to deploy an MLflow project to a compute instance or a compute target. If you're interested in staying just Azure ML, the closest idea here is the notion of pipelines, which I'm going to talk about in a moment. As far as the model registry goes, we have in Azure ML the ability to store different models and different versions. Looking over here on the left-hand side, what I've got is a lot of different versions of projects and different versions of models, excuse me. So we have the experiment that created it, but we have the name and version of the model and when it was created. So I can track these, watch them over time, work with them over time, and even drill in and see that models will contain stored artifacts. So here I've got inside outputs, I have a model.pickle file. So that is a serialized version of the machine learning model itself. And you can also store helper files. With many neural network projects, we tend to have things like H5 weights. And we're going to store those in our model output as well. Models also contain information on the data sets that were used to train, including links to dataset and version. That way you can see what version of data was used and get into some of the notions of, well, you're not allowed to use certain information, legally speaking, in some circumstances. A classic example of this is that if you are, say, lending money for purchasing a home in the United States, it is illegal to consider the candidate's race as a factor for whether or not you'll loan the person money. And so we can show in our data set that we have no model attributes that are related to race in here. Once we've got a model in place that we like, this is pretty easy for operations staff to deploy it. There's a UI version as well as, of course, a code version. If you're using the UI, you click the deploy button and we can say deploy to a web service and send it out that way, or deploy to a real-time endpoint, which is currently in preview, public preview. So with that, let's now move on to machine learning pipelines and learn how we can take that code-first programming mindset and turn it into a flow, a process. Azure Machine Learning is built around this notion of pipelines. We have this concept of data cleansing, data transformation, model training, model scoring, model evaluation. These can be different steps of a pipeline. And so we can perform, for example, data transformation and data training as part of an inference pipeline as well, allowing us to generate predictions. One of the benefits of doing this in a pipeline is different people can work on different steps of the process concurrently. So when we use the designer to train and deploy models in Azure Machine Learning, what we're really doing is creating pipelines. This right here is a pipeline, and you can see the UI, you can see the inputs feeding to the next component. So why might we want to use pipelines? There are several reasons for this. The first one is source control. I'm going to be able to script the code that I need for source control. And that way, if I need to deploy it again later, I'll have it available to me. I can control deployment on local and remote instances of compute. I can separate out areas of concern. So for example, my data engineers may work on data prep. They may work on trying to clean up the data, the scripts necessary for that data prep. I may have data scientists focused on the specifics of training prepared data. I may have operations people who are writing code specific to taking the trained model and deploying it. And I can have 3, 4, 5 separate people working on the same project at the same time because they're in different files, in different components working together. We can also use heterogeneous compute, meaning that if I have a training task which makes sense to use GPUs, and I have other tasks which don't make sense for GPU, I don't need to pay for GPU compute the whole time. I can say, perform this training step using GPU compute, perform this data prep step using CPU, and save some money. For very large data sets, that can make a difference. I can also collaborate on data science projects, making this a multi-person, full team effort, and reuse components between pipelines. So what I can do is, if I have a data prep step for this training, and I have another model that is going to take roughly the same data, I can use that data step component, that preparation component, and reuse it in the other model as well, in the other pipeline. That is going to save you time if you're in a large enough organization where you have a lot of overlap in what these models look like. If you want to execute pipeline code from Visual Studio Code, we are going to need Python installed on the machine, as well as the Azure Machine Learning SDK. And you'll also want the Azure CLI, most likely. The easiest way to get the Azure ML SDK is through pip install Azure ML Core. And I also recommend probably using the Anaconda distribution of Python for this, because you can certainly get by without using Anaconda. You could install packages yourself, but Anaconda has so much already installed around pandas, NumPy, scikit-learn, and other libraries that you're going to find extremely useful when working with Python. Let's see, now that we have in mind what a pipeline kind of looks like, how we could take the code that we wrote in a notebook and convert it into an Azure ML pipeline. To do that, I'm going to do a few different things. We're going to move training code into its own separate Python file, and we'll execute it as a Python step scripts. Then we'll separate out some code and run the pipeline, and separate out code to register the resulting model. So let's go to our next demo where we're going to do just that. In this demo, we're going to take the code that we created before with these expense reports and convert that into a one-step, fairly simple pipeline. This is the notebook that I had before, and I don't really need to have it open anymore. I could keep it open for reference, but let's walk through the expense reports pipeline. This is a pretty straightforward pipeline. You will need to install Azure ML Core and Azure ML Pipeline pip packages. If you've done that, you can execute this. Everything will load and you'll show your version of the Azure ML SDK. Then connect to a workspace. In the event that you don't have a config.json here in .azureml, you'll perform workspace.get, enter the name of your workspace, so whatever the name of your Azure ML workspace is, your subscription ID, and your resource group, and then write that to config.json. I already have that, so we can execute this, and we'll see our workspace name, region, and resource group. Next step, I want to create an experiment called Expense Reports Pipeline. That experiment will register what we're doing. We'll have a script folder, source, and a temp folder, TMP. I actually have a source and temp folder right here already. Shows that I've run this before. We're going to create a CPU cluster. This is standard D2V2 up to 4 nodes. A lot cheaper than running on GPUs. And because this is a fairly straightforward, simple demo, we definitely don't need GPUs. We couldn't take advantage of them given our regression model, even if we wanted to. Let's perform datastore.get and grab the expense reports data store that we created well before this demo. First step, data preparation. Now, this is where things get a little tricky with pipelines. Pipelines expect files to be read and written. Because we're dealing with a SQL database, it gets a little weird. So what we're going to have to do is take the SQL database and convert it to files. So let's grab our query prior to 2017. We'll grab our data types, specify our expense report to a pandas data frame. And this includes all of our data. Then we have a local path is temp folder plus expense report CSV, and we're going to write to there. So I just wrote to that file. If I load up that file, we have a bunch of rows with our expense report information. After that's done, what I'd like to do is upload this to an expense reports folder on Azure Blob Storage. It's already up there, so I don't have to rewrite it. But it'll be in a folder called expense reports, and it's going to be called expensereports.csv. And then we're going to load this expense reports CSV data set from Azure Blob Storage. It's a lot of messiness just to get to the pipelines, but pipelines really want to work with files and folders. So our next step is to train our model. We're going to get an environment, and in Azure Machine Learning, we have the ability to specify our own environment. I can use a conda dependencies file, for example, that specifies what I want the shape of my systems to look like. Or I can use one of the built-in environments. And I'm using one here, Azure ML scikit-learn on Ubuntu 18. If I pop up here to environments, we can see all of the environments that they currently have available. And scikit-learn 024, the one that I'm going to use is this one right here. My next step is to create a script run config for training data. So script is train.py. Let's take a quick look at that file. Inside here, I'm going to perform a train test split. We'll do a decision tree regressor, so similar type of regression model as before. I'll get a new run and grab the input data sets, prepared expense report DS. And where we're going to get that information is actually in this next Python script step, where my expense report CSV DS will be called prepared expense report dataset. So let's execute that, return back to our training script, split the data into training and test. Both of them will be pandas data frames, and train on our training data, expense category ID and year as the inputs, amount as the output. We'll build out our test results and generate metrics very similarly to what we did before. Root mean squared error overall and root mean squared error per employee and expense category. Once I'm satisfied with the results, I'm going to write out the model.pickle file to outputs in my run. And that's what the training does. So we build a pipeline. The step will be train step. The major benefit to using a pipeline in this case, even for a really simple case, is my data scientist can write this train.py. And as a data engineer, I'm just responsible for making sure that I can execute the code, making sure that I can set up the compute for the person. So we might have two different people writing this code versus our original notebook, which really you could only have one person working on it. So this way you can separate out the work a bit and make it a little easier for people to specialize in what they're best at. We can wait for completion, and I'll select that. You can see that the pipeline status is currently running. But if I come over here to experiments, we have an expense reports pipeline, and the latest run is 23. If I pop this open, we are on a training step. Now, this is going to take about 4 or 5 minutes for the Docker image to get set up appropriately. So what I'll do is pause, and we'll return once this is complete. And our run has completed. So we have our steps here, the training step. I can look at different outputs and see, for example, the driver log says, yep, everything was successful. So our metrics, we have outputs from here. Things are looking pretty good. And if I pop back to here, took a little while, probably about eight minutes or so to finish up. Next thing I want to do, register the input data set and the output model. So here's what the input data set looks like. This was from Workplace Blob Store, expense reports / expense reports.csv. I had taken this file, uploaded it to Azure Blob Storage, and made it available up there. Next, I want to register my data set and make sure that it's now available to everybody. And now I want to register the model and call this expense reports pipeline model and run this thing. And I've created an expense reports pipeline model. Select models. We can see that model here, version 2. I can choose it, and we do have some artifacts, specifically model.pickle. This is going to be nice because I'll be able to deploy the ML pipeline for expense report estimation. And for this, I'll have a web service, local web service, and also going to Azure Container Instances. The first step is to load our config and pull in the expense reports pipeline model. This is going to get us by default the latest version, version 2, but you could specify another version as well if you so choose. Just as with model training, I'm going to need to create or get an environment. I've decided to use the same scikit-learn because it also has the Azure ML SDK on there, and I'm going to need it for scoring. I'll next create this inference config and deployment config. Inference config says every time somebody calls your web service API, send them to score.py. And score.py has two methods, init and run. The init function loads a model, expense reports pipeline model. So we pull that thing in. And the run function takes in some raw data, deserializes that data, converts it to a data frame, generates predictions based off of expense category and year on the model that we've loaded, and returns the results as a list. To test this, we're going to run it locally on this machine. So the name will be expense report score local, using our model, using that inference config, and the deployment configuration that is a local web service on port 6789. This will take a moment. And by the way, you do have to have Docker installed and configured for this to work. I have Docker for desktop running, and we can see the different steps. And it says that the container, checking to see, yep, the container is running at this URL. So let's pop over to Postman and send in a request and see how it works. Here we are in Postman, and I'm going to zoom in a little bit here. Going to localhost 6789/score. In the body, I'm going to pass in this information that we may need. In reality, we only need expense category and expense year. But just in case you wanted to send all of the info, you would send it as this array called data. And we're going to make sure that the content type is application JSON. Send this along, and what we get back is, for each element in JSON, here is the predicted expense amount. So looks like the service is working when running locally. This is an important step because it is really hard to troubleshoot deployments. It's really hard to tell if the problem is in your scoring file, if the problem is in your configuration, because you don't get much info. If you run it locally, you can check the Docker logs, and that will give you a lot more information and help you out with troubleshooting. So once you're done doing all of that work, we can create a new deploy configuration that goes on Azure Container Instances. And for deploying to Azure Container Instances, most of this code stays the same. The difference is ACI deployment config instead of our local deployment config, and I gave it a new name. The benefit to this is you can think about model deploy. If we're in a local branch, maybe we push it out to a local Docker container. If we're in a dev branch, we can push it out to ACI. If we're in a prod branch, we could push it out to AKS, and the code would be the same. We just have a different name and a different deploy config as input parameters. This is going to take a moment to get the deployment going, but what I'll do again is pause and return once it's ready. In this case, it took a couple of minutes to finish up, but I've got a URL. So let's copy the contents of that URL, and we're gonna paste it right in here in our post operation. And I should expect to see pretty much the same results, and I do. So that shows that our deployment successfully worked. By the way, if you want to see this over here in the studio, we can go to endpoints, and I can see the expense report score ACI endpoint right here is running in a healthy state. So I could actually test it up here. I could consume it. Everything's up, ready for me to go. Welcome back. We are now going to talk about machine learning operations. MLOps is a better way of deploying code. And a development that we've seen in software engineering has been this progression, this automation from everything is manual, especially UI driven, to kind of code-based but still manually executed, to deployed using semi-automated solutions, to full-on CI/CD deployment operations. And this progression is also true in the machine learning space. We're seeing organizations move from that basis of everything's got to be manual and getting them toward more things automated. Machine learning operations is built off of many of the principles of DevOps, but it's really tailored to a world where it's more than just code. DevOps in many cases is about deploying code. I have application code that I'm going to deploy out. I have server resources that I'm going to store as code, YAML files or JSON files or ARM templates, and push those out. But at the end of the day, all of this is still considered code. It's relatively small in size, and ML is not really quite the same. You do have the code. The code is important, but the data is critical, and the models themselves can be quite large. We may be talking about gigabyte-sized models, certainly not the type of thing that you would check into a GitHub repo. Also, one of the key problems in MLOps is really automated retraining and deploying. It's not about getting the code out there once. It's about what happens after the code is out there and we have new data. Well, now we want to train a new model and potentially replace the current model that's there. That's where we get to machine learning operations. And there are different MLOps maturity level models. Microsoft has one, Google has one, other organizations have them as well, of course. Of the two that I mentioned, Microsoft's is more fine-grained, so we're going to look at that model. The Google model has very broad agreement with the Microsoft model. They both agree that here is the starting point, here is the ending point, and here are steps to get there. But the Microsoft model kind of makes it a little bit more, let's walk through a little piece at a time. So we have right here our initial maturity model, no machine learning operations at all. Basically, data scientists work on their own machines. They're not really talking to anybody else. You probably don't even have data engineers. Software engineers get the model from somebody else. Like a data scientist says, okay, here's a pickle file, go deploy this, please. You gather data manually. You're often running this compute from a local machine, and model release is manual, scoring is manual. You're really doing everything manually. As you get to the first step along the way, you start talking about DevOps, but not necessarily MLOps. So you still have many of the same personnel problems, but at least you have some of the processes being deployed automatically. You have, once code is checked into source control, then it is deployed out to a relevant environment. However, model release is still often a manual process, and you're still heavily reliant on data scientists to figure out how to get this right. The next step along the way starts to automate training. You're tying people together a bit closer. Your pipelines are more managed, so you're tracking experiments and tracking runs of experiments checking to see if your results are different from your prior runs, but you're still manually releasing. So it's not automated everything. It's more of training the model is automated. However, there's a human gate which is going to still be there to say, I don't think I want this out, and when I do want it out, I'm going to take the model and manually deploy it out. The next step in the process is automated model deployment. You continue to have more tests as your experiments are going. You don't necessarily have that human gate anymore. Instead, you have checks. Here is the quality of the current model. Here is the quality of the new model. If the new model is better, go replace the old model with it. We don't need a human to say, oh, yeah, go ahead and do this thing, because we have built enough tests, we've built enough checks to ensure that based on whatever relevant scoring criteria we need to use, this model is better than that model. Finally, MLOps, automated retraining. We have everything flowing, going as we want it to be. Everybody's cooperating together, working directly with other teams to make sure that all of the pieces are repeatable, that all of the processes are well defined, are laid out, tests are created. Retraining happens whenever, for example, you have new data generated, or maybe on production metrics. Hey, I've noticed that efficacy has been dropping lately on this model, so let's automatically retrain and see if we can replace that model with something better. Scoring scripts are version controlled along with the tests. You can track over time historically how your models have scored and even be able to compare older iterations of models. A common problem in machine learning is that we're chasing noise. So in other words, I may have a model which is good, and then I train something that looks better, and then I train something that looks better, and I train something that looks better, and eventually you find out that that first model actually is now the best model. So you're kind of going in this circle of bouncing around between models because you're not actually getting something better. You're simply chasing the noise, and at this moment, this model is better. And that's what we can learn using automated retraining and do a broad-based comparison to older versions. If we're not consistently better than these older versions, then let's not deploy something out. Let's alert the machine learning team. Let's alert those data scientists, and then they'll be able to investigate further. How do we get to there from our beginnings, though? And what kind of tooling is available? In the Microsoft world, in Azure ML, we have Azure DevOps and we have GitHub Actions. Both of them are going to give you capabilities to do model CI/CD with Azure ML. I'll give you a brief rundown of an example using Azure DevOps. So I have directly above me here a few pipelines that were created. These are MLOps pipelines, not ML pipelines. Pipelines are a pretty heavily used metaphor, and I want to differentiate the two different types of pipelines that we're talking about here. The first type is the Azure ML pipeline, code, training, and scoring models. The second one is Azure DevOps pipelines. This is building and deploying code, running unit tests, deploying out code, and that code is the Azure ML pipeline. So that's where the confusion can come in, but they are different things. So here's the process in a nutshell. Step one, we're going to create what is called a variable group. And if I move over here, we can see right up here the different variables and values that have been set for those variables. Obviously, for different projects, you may need different sets of variables, but this is going to include where are you deploying it to, maybe resource groups, Azure ML workspaces, locations of different setups. If you're deploying it to Kubernetes, what's your AKS cluster, et cetera, et cetera. We can then create an environment. So this is an example of a pipeline that creates an Azure Machine Learning workspace and associated resources. This will let you recreate your environment after a disaster without any manual intervention. If I destroy the workspace, maybe somebody just deletes the workspace, not realizing we need it, I can have this pipeline that recreates it. And it's all based off of YAML. We're not going to dive into the specifics of the YAML here, but basically, I will mention a couple of the points marked out in red. So at the very top, we have a trigger. Whenever the master branch updates, then I want you to trigger this pipeline. The pipeline will grab code from the master branch in specifically the environment setup / ARM templates folder. All of the code in there. And we're going to create a deploy agent using Ubuntu. We'll load the variable group and even set some additional variables like workplace SKU. Then execute an ARM template, that is cloud environment.json, which will build out the relevant resources, the Azure ML workspace, the storage account, the key vault, everything that we need in order to use Azure Machine Learning. After we've done that, we can train a model. And when code is checked in, we're going to kick off a pipeline that will run some unit tests on the code. So that is the first step right here. This is continuous integration, running unit tests, making sure that everything looks right. If it looks right, then we'll run these steps to train and evaluate the model, and if it's good enough, publish the artifacts. When it comes to training a model, a couple of quick notes. The first one is that agents are going to be built from a particular container image. In this case, it's the one that I have up above there, the MLOps Python latest. Your scenario may be quite a bit different in terms of the container image you use. The trigger for when this executes is when specific files or files in specific folders are modified. And in the event that these files are modified, that's when we're going to need to kick off another training. So if I change the way that I build my models, or if I change the data that I'm using to train the models, then we want to execute a training operation. The stages are going to take us through the different steps along the way. We're going to have 2 stages. And I know that we have 2 stages because we have, one right here and one right over here. The first stage is modeling. It's the model continuous integration. The execution steps themselves will be stored in a different YAML file. That way, you can have, again, different team members working on different parts of the problem concurrently. And in this case, the code quality template is essentially what are the unit tests that need to be run in order for us to say that, yes, the training code is valid code. If I go down through this code template, I will point out that folders use dot instead of a slash to indicate whether or not you're in the right directory. So ML service dot pipelines dot diabetes regression build train pipeline is really going down into the different levels. We can also see that what Azure DevOps is doing is really just running Python from the command line interface, executing a script, and based off of the return results from that script, will decide whether or not to continue to the next step. And this next step, if the prior one succeeded, is to train and evaluate the model. Well, to do this, we'll have multiple jobs. And a job is one of those components within a stage. And if I go back to the image, I have 3 jobs up in this train and evaluate. So the first one is to get the pipeline ID. Again, using the Azure CLI, we're going to get the pipeline ID and then pass that to the next step. Well, that next step executes an Azure ML pipeline. So it's not just running some code. It is kicking off a pipeline that has been published via Azure ML, invoking it, sending in the relevant input parameters, and in the event that we get a result, publishes a new model. In this case, we're just going to publish it if the prior step completes. But we may have other restrictions. We might have a script here which runs and says, is our model significantly better than the existing model in production? If so, publish it. If not, don't publish. We may have checks against prior models to make sure that we're not in a situation where we're chasing variance. This level of sophistication is something that you would have to develop yourself, but it is possible. When it comes to deploying a model, we've trained it, but we can automate deployment as well using another Azure DevOps pipeline. In this case, the sample here is 3 separate steps. Deploy to Azure Container Instances, deploy to Azure Kubernetes Service, deploy to Azure Application Services. If we want to deploy a model, we may base this off of variables. Do you have a variable set for deploy to AKS, for example? And maybe it's set to false. Don't deploy it here, and so it doesn't deploy. So now let's wrap things up by talking about scoring on Azure SQL Database. Azure ML is really a file-heavy experience, as we've seen throughout this talk. It is a lot easier to work with files than it is databases, and I think that's a blind spot for the product. This is painfully obvious if we're trying to write prediction results to Azure SQL Database after running scoring. In this final demo today, we're going to write to Azure SQL Database. This is not nearly as easy as I think it should be. We're going to have a simple notebook to write to an Azure SQL Database. So let's look at the code. I'm going to load up some of our standard Azure ML core objects, our data objects, as well as pandas. And then I'll load our workspace from configuration. Pretty easy, not a big deal. I'm going to need 2 stores here. One is my expense reports data store. The other one is a blob storage work store. So let's pop that up. And then query our data. Let me briefly hop over here to Azure SQL Database just to give you an idea of the table we're going to write out to. So we'll have this table called Expense Report Prediction. And let me drop and recreate that table. I want to show you that there are no rows in there. And this table will store our expense reports input as well as the predicted output for that expense report. My query here will look at everything prior to 2017. And we'll look at this data set as a tabular data set from a SQL query. So let's run this. Converted it to a pandas data frame. It was a real simple query to run. No big deal. Just a quick reminder of what's in this data set. We have our employee, we have expense category, we have date and year, and then we have the amount. I'm going to switch to a different model. This time it's a random forest regressor. So last time we did some code, it was decision trees. This time it's random forests, taking an expense category and year, giving out the amount. And I'll also have a query that is from 2017-0101 forward. So we have our test data set in this case. So let's generate predictions, and we'll generate predictions the same way that we did before. We'll call the predict function, passing in expense category ID and expense year, and create a new output that we call predicted amount, convert it to a single column data frame, and then append that data frame to the input test data. So that way we have our end results, which are base inputs, and then the predicted amount. Now, I want to write this to Azure SQL Database. There is no simple write data set for Azure SQL Database. The thing that we can do is take a tabular data set like what we have right now and convert it to files, and then use Azure Data Factory to move the files over to Azure SQL Database in this case. Let's get started on that. We're going to create a folder called data on our local compute and write a file called predictions.csv, and we'll output our data. I have a terminal open here, and let's clear that. Here we're in our data folder, and we can see predictions.csv. I'm going to check LSLA, and I have no other files in here, which is good. So my predictions.csv, and if you're interested, we can do head and look at the first few rows. It's a simple comma-separated values data set. Then I'm going to upload this to blob storage in a target path called expense report prediction. So I run this, and it actually already existed. Next step, I'm going to build a pipeline. And this pipeline will include sending out a request to Azure Data Factory. So to do that, we're going to bring in my Azure Data Factory. So here's the name, CSAZDF. It's in the CS Azure ML resource group. And the ADF compute that I've already created, AML compute ADF. So we're going to attach a compute target and wait for completion. So let's run this. Because I've already set this up, provisioning was really fast. Otherwise, it may take several minutes to finish. I'm going to create a data reference to bring in Azure Blob Storage, specifically that workspace blob store that we have in the expense report prediction folder. So we're going to mount this folder as prediction blob ref. Bring that up, takes a very short amount of time. Then I'll have a SQL data reference. So my SQL data reference points to the expenses data store and will be called prediction SQL ref, and will write out to the table expense report prediction. The data transfer step is how we're going to take data from Azure Blob Storage and put it into Azure SQL Database. We have our source of the blob store. We have our destination of the Azure SQL Database. We're going to use ADF compute as our target, our compute target, the machinery that will do the work. And our pipeline will just be a simple single step that says transfer that blob storage. So we write this and got that all set up. So we've primed the pipeline. Now I can set up an experiment and allow it to run to completion. Let's do that. We're writing things out, and as we're going at this, I actually have up Azure Data Factory, and we can see a couple of runs that I've done of this. Here's my current run of it. If I collapse these, we can see that it's currently in progress. In case you're curious about the failure, I had a couple of extra files in that data folder. That's why I went and made sure there was nothing else in that data folder. I can query it in Azure SQL Database and get back 2,699 results, which is the number of rows in that table. I know that it's the number of rows, by the way, 2,699, and all of my predictions and my amounts. I know it's the number of rows in the table because in the data output, if I do a word count number of lines, I'll get 2,700, but I know that there's a header, so 2,699. Welcome back from our demo. Let's do a little bit of wrapping up now. Over the course of this talk, we've looked at different ways to take Azure Machine Learning, starting off at this sort of drag and drop UI, introducing code first programming, introducing ML pipelines, including ML flow and its ML analogs, and seeing how ML ops can help us automate our deployments that much more effectively. If you would like to reach out to me afterwards, feel free to hit me up via Twitter or via email. If you have consulting questions, happy to take those as well. Hit me up at that URL. I want to say special thanks to Microsoft for supporting Data Platform Geeks and SQL Server Geeks community initiatives. And also, make a note that there are 3 ways to win prizes today. So be sure to post your selfie with that hashtag up here. You can also give feedback on this session as well as the entire conference and check out sponsors and exhibitors. So with that, I'd like to say thank you so much for attending and hope you have a great rest of your conference.